Today is a sad day. Many math students never make it this far, or they will say, I don't get it, because this topic is too hard. Let us remember their hard effort as they fail the AP exam. That's right, we are going to go over this topic and make sure you all understand whether you like it or not. Here we go. Look at this. Yeah, look at it. Who? What is that? 3 dimensions? Absolutely right. They will be asking this on the AP exam for volumes of cross-sections of different shapes and the total volume that results from it. Oh, how do we do that? Exactly. This is why we're going to spend the majority of the rest of this month and even bleeding into April for us to truly understand what in the world is going on over here. All right, so are you ready to really learn the last moments in your AP Calculus life here about what really kills all of these students on this exam? So we have now, instead of dealing with just 2 dimensions of just X and Y, we will now be increasing this up to the 3rd dimension, which will then result in a volume that we can still integrate across limits on the X and Y plane. That is absolutely right. We have a lot more to keep track of and more equations that they will not give you on the exam, but you are expected to memorize. Now, without any further ado, let's see if we can find out what is happening if we were to take a quick example of something like this. We have ourselves our graph right here, and we are going to take it in terms of f of x being equal to x squared minus 4. Something very simple that we can follow along with, and we can then see what it looks like in terms of what they're asking us to do. So a quick graph of x squared minus 4 will give us something like this in a lovely parabolic shape here. Now, what if the question then asks for something like this? They are asking to find the volume if the cross sections that are perpendicular to the x-axis are squares. Okay, and of course, in this case, they are asking specifically for the volume bounded by f of x and the x-axis, right, from -2 to +2. Okay? They will tell you exactly where they want to find this area. So in this case, with that area that we can easily define on this graph, we are going to bring that forth onto the 3rd dimension to then find its volume. So because of this, we can take a quick note here that if we're going from -2 to +2 on the x, between the x-axis and the graph of f, this will be the area in which we will be extruding to that new dimension. Now, the issue is that when we graph something like this, it's not necessarily the easiest way to see what this looks like when we bring it forth, again, in the 3rd dimension out from the board. So, just for the sake of this problem, if we were to make some sort of 3-dimensional graph just to visualize this, us going across, again, that's the x-axis and that is the y-axis over there. So, we do something like this, coming across, and then, like I said, the cross sections are perpendicular, so we will cut across into the nice sections of the area, perpendicular to the x-axis, and then we lift it up over the z-axis, the 3rd dimension, as we go across. Now, this isn't necessarily the easiest drawing for me to do. Again, the one back there is a lot nicer in terms of seeing how these squares are lifted up higher across the board here. Again, remember, the idea is that they are squares. My drawing might not be the best, but that is indeed what the problem is telling us to do. So then, how could we find volumes based off of a geometric shape? Well, think about this. Something that we have done before is that if you integrated a singular line across some sort of limits from A to B, right? Every time we integrate it across a line, which is going to be in the first dimension, after taking the integral again, we find again, as we say so many times, that an integral is simply the area under the curve. Well, that just means that our resulting area coming from a line is that we went from the first dimension, and then the answer itself will be resulting in the second dimension. Ooh, yes indeed, we are increasing the dimensionality of this function here. Now, in terms of going to the third dimension, what if we think about it this way? If the cross sections are squares, again, meaning that we have a square coming up off of the xy axis, again, the vertical going the f of x, the results of the function. But because it's a square, the vertical height is also the same exact length as well, the result of that same function as it travels across. Well, if our limits are going from a all the way to the final part of the function, if we were to imagine it as something that's a bit larger, so going to b for that same function, well, if we were to integrate all the squares along the way down that path, would you look at that? If we were to take an integral of an area per se across the function, well then that will give us a volume coming out in the starting from the second going into the third dimension. Oh yes, this is exactly how we are meant to visualize this kind of a problem. Okay, and so because of that, there is indeed an equation we need to abide by. Going back to our first square again, the length and width of any sort of square will be exactly the same across either side. Again, no matter which part of the function you go through, the width and height will always be the same because they defined it as a square. So in this case, for this function right there, f of x, again, our volume now will be defined as our limits going from -2 all the way to +2 on the x part. Then we will have x squared minus 4, that function, but now we must square it according to x. Again, we have the length and the width both multiplied to each other, and then we integrate across us going down the path from -2 to +2, and by adding all of that up, thanks to the summation of any sort of integral, we are adding up all the individual squares going from -2 to +2, making ourselves a nice three-dimensional volume. And that is exactly what they want us to do. So let's quickly run through this integral so that we know what we're dealing with. At least in our part, we just need to FOIL out the x squared minus 4. So we just do that really quickly with some very standard algebra 1. Then we can integrate accordingly. So this gives us x to the 5th power over 5 minus an 8 over 3x squared plus 16x. And we evaluate from -2 to +2. And so because this is now a simple definite integral exercise, all we need to do is plug in the upper limit subtracted by the lower limit. And so again, I have the work all done right here. So in any case though, with just the practice that all of you have already done at this point, we end up with a total area of 512 over 15. Again, this is going to be a volume, usually in some units cubed. Okay, so again, this will just be a little bit of additional exercise for the definite integral, but we end up with something like this. Not so bad for what we have so far. Again, we can go over all the steps individually, either during my live stream or when we return on Monday with some more example problems. But let's quickly go over to one other scenario and equation that you will need to know right about here. And so we have a little change to the problem if we were going to ask, instead of squares, into right triangles. That's right. We are going to change the shape, which of course will change the volume as we integrate across. Right triangles? Well, let's think about that. Right? If we had, instead of a full square going across, what if instead we just had a right triangle? So it goes horizontally and then vertically in terms of the f of x right there. And then we just go diagonally across. Again, maybe in a better light here. So again, the idea being that we have multiple right triangles going across the limits, the base and height both being f of x. Okay, now what would that mean for us? Well, in our case though, think about this, right? If it were a right triangle, well, that makes everything life a little bit simpler given the fact that a right triangle is simply a square cut diagonally in half, which just means that we will end up with a similar volume as the volume of any sort of cube, and cut exactly diagonally, 2 equal parts, makes it exactly 1/2 of the area of normally a square. And of course, the area of a right triangle will follow exactly the same, of it being a base times height multiplied by 1/2. So in this case, in a right triangle scenario, all we need to do is keep that 1/2 coefficient for the same exact function. Now again, all of that squared, because it's base times height, they're exactly the same in terms of it being an isosceles right triangle of both f of x vertically, f of x horizontally, and we integrate across the axis. And so, because of that, we end up with something like this, which thankfully we've already done all the work before. We already know what the squares look like in terms of that volume. So if all of this was exactly the same as the 512 over 15, well, that just means we need to multiply across it a simple 1/2 coefficient, just so we can slice that volume exactly in half. And then we end up with the resulting 256 over 15 volume for the triangles. Not so bad at all, okay? And so something like this, again, it seems very daunting at first because we still have many other things to go over during this section, being rotations and a few other shapes of cross-sectional area. But nonetheless, though, this is indeed something that will definitely be on the exam in a few questions. And of course, all of our students need to fully understand what these questions are asking for, especially if it shows up on the free response exam. And so with this should wrap it up for what we have today, just as a nice introduction to what we are dealing with in terms of some cross-sectional volumes that we need to discover. So with that, we'll be back on Monday with some more example problems. We'll go through multiple steps of this process, and we'll see you again next time.